Well, hello again, and thank you for joining Complex Variables. And we're going to finish up today. Literally, this will be the last lecture because on Wednesday, I want you to have an opportunity to work on your take-home final to make sure that you finish well. So this will be our last class. So I'm going to really hustle through things. Let's pray and let's go. Father, thank you again for another beautiful day and another opportunity to talk about the wonder of your mathematical creation. And I pray, Father, that this class in complex variables has been extremely helpful to people, that they've seen a new side of the world, and that it will help in their mathematical career. Thank you for each student. Father, keep them well and continue to bless them through their lives. In Jesus' name, amen. Last time, we talked about the fact that a function that is analytic and has a non-zero derivative is actually a conformal mapping, which is magic. That means that it preserves angles from input to output. And that's a big deal in physics and a number of other fields, any place where you study harmonic functions. And I recommend that you go to Wikipedia or someplace and check on harmonic functions and see where they're used. They're very useful in other fields other than mathematics, but my interest is in the beauty of the theory in mathematics. So what I want to do today is I want to discuss how other fields of mathematics would use it. I'm going to talk about the fact that if you have a harmonic function and your mapping is conformal, then when it comes out the other side, it's still a harmonic function. Now, what do I mean by that? You remember that one of the primary uses of the idea of conformal mapping is to take some funky region where maybe you want to know the temperature through that region, you want to know electric potential, whatever it is that you want to know through this, either a plate or a region in the plane, that if you know its values on the boundary, and if the function is nice, if the function is harmonic, that property shoots over to the nice region that you map it to. Pardon me, ending a sentence with a preposition. But I need to prove that, and it's very easy to prove, but it's a long proof. So strap your seatbelts and let's get going. So let's see. Let me remind you of our key point. If f is a function that maps a region to some other region, where, say, f is equal to u plus iv, and f is analytic, then as long as the derivative is not zero, through the region, then t sub xx plus t sub yy equals 0 in the original region if and only if t sub uu plus t sub vv equals 0 in the other region. Okay, so that's the idea. And the whole principle behind this is if you've got a problem that you need to solve, but you've got a strange region that's kind of funky shaped, and you'd rather do it, say, in the unit disk or someplace that's more controllable, you want to make sure that the harmonic feature of the function is maintained. And so if it went in harmonic it comes out harmonic. That's what we want to prove. Okay? So, let's prove this little guy. If u, as usual, is u of the input variables x and y, so it's a real valued function of two real variables, v, same thing, is v of xy. And if they are twice continuously differentiable, in other words, I can take partial derivatives down two layers, and those partial derivatives at the second layer are continuous. Then what is the derivative of t? Now t, remember, is a function of x and y. And that goes over to u and v. And so u is a function of x, v is a function of x, each one of them is a function of y. And so if I take the derivative of t with respect to x, then by the chain rule, that's the derivative of t with respect to u times the derivative of u with respect to x. But I also have to worry about v. That's the partial with respect to v times the partial of v with respect to x. That's how you do the chain rule in two variables, okay? Thus, if I take another derivative, t sub xx, that's equal to the partial with respect to x of this. Which is equal to, now the derivative of the sum is the sum of the derivatives, so I can do them separately. That's the partial with respect to x of t sub u times u sub x, plus the partial with respect to x of the same thing for v, t sub v times the derivative of v with respect to x. Now, how do I take this derivative? That's a product of two functions, so I need the product rule, okay? So what is that equal to? That's going to be equal to t sub u differentiated with respect to x times u sub x, the derivative of the first times the second, plus the first, t sub u, copy, copy, times the derivative of the second, which is u sub x differentiated with respect to x. And I do the same thing for v. It's my t sub u differentiated with respect to x times the second, derivative of the first times the second, plus the first times the derivative of the second, which is u sub xx. Okay, so far so good. Now, what is this? This is equal to, in order to differentiate this function with respect to x, I have to do what I did up here, namely differentiate it with respect to u, multiply by u sub x, and okay, so I have to use the chain rule here, so that's going to be the derivative of t sub u with respect to u times u sub x plus, and the same thing for v, u sub v times v sub x, and that is just that part. So now I have to multiply that by u sub x plus, and here I just copy, t sub u times u sub xx plus, and now I have to do the same thing with the chain rule here that I did before. So I've got t sub vu let's see, let me make sure that I did that right. No, this is V. My apologies. Go up one line. You've got T sub U parentheses sub x times U sub x plus T sub U, U sub xx plus T sub V times V sub x plus, and so that's T sub V differentiated with respect to x times V sub x plus the second derivative with respect to V times the, make sure I've got this, and V sub x plus T sub V, just one derivative with respect to V. V sub xx. I should write larger so that I can read it. Audrey, would you help me write bigger? Okay. So that's equal to, all right. Now I use the chain rule, T sub u times U sub x plus T sub uv times V sub x. All of that is multiplied by U sub x, okay? Plus T sub u times U sub xx. Just copying that from above. And then down here I do for V what I did before. I've got T sub VU times U sub x plus T sub V with respect to V times V sub x. And all of that is multiplied by V sub x. And then plus, just copy over that last term, T sub V times V sub xx. There we go. All right. So now let's multiply everything out and see where we're at. Okay. I've got, now here's how I'm going to arrange this. I'm going to take this term first, T sub U times U sub xx plus, now, T sub UU is multiplied by U sub x squared. So I'm going to take care of that term next. Okay. The next one I'm going to do is T sub uv times U sub x times V sub x. So that would be this one, T sub uv times the product of the two partials. So plus T sub uv times V sub x, U sub x. Actually, I'm going to write it in the other order just because I've got this alphabetic hang up. You know, math doesn't know the alphabet, but I do. Just all right, now the next thing I'm going to take is T sub V, V sub xx. So that's T sub V, the last term here, T sub V, V sub xx. So plus T sub V, V sub xx, plus, now I've got a T sub VU, U sub x, V sub x, times U sub x, V sub x, okay, plus, I don't have room on there because people have told me it's hard to see that corner, T sub VV times V sub x squared, okay, and all of that is T sub xx. But I also need T sub yy, but by symmetry, I can replace all the x's with y's and just copy them down. So T sub yy is equal to T sub u, U sub yy, plus T sub uu, u sub y squared plus t sub u v u sub y v sub x, v sub y, plus t sub v times v sub y, y, plus t sub u, u, times u sub y, v sub y. So that's t sub y, y. Let's see if I have the right number of terms. 1, 2, 3, 4, 5, 6, 2, 4, 6. One missing. T sub u sub y, y. T sub u sub y squared. T sub u v times u sub x v, u sub y v sub y. T sub v sub y, y. T sub u sub y, plus, the tail is a very important part of the dog. V sub y squared. Okay? Now, when I add those two guys together, and I call this equation star, so 0 is equal to 2 sub x, t sub xx plus t sub yy, which is equal to, okay, now, here I've got t sub u times u sub xx plus u sub yy. Is that the way I want to bunch these together? Maybe not. So we'll see. So this is t sub u times u sub xx plus u sub yy. Yeah, I do want to bunch those together. Plus t sub u. So I'm just copying over the sum of these two. And I've got, that one's multiplied by u sub x squared plus u sub y squared. And then plus t sub uv times u sub x v sub x plus u sub y v sub y. A lot of this stuff is going to turn into a pumpkin very soon. T sub v times v sub xx, believe it or not, we're close to the end of this proof, plus v sub yy, plus t sub vu times the quantity u sub x v sub x plus u sub y v sub y, plus t sub vv times v sub x squared plus v sub y squared. Okay, and that's the sum of all of them. Cool. Now, here's the good news. But F is analytic. Now I'm going to pause you while I go turn on the air conditioner. It's hot. Okay, I'm back. Now, remember that F is analytic, which says that, for example, u sub x, x plus u sub y, y equals v sub yx minus v sub xy. And why is that? Because u sub x is the same as v sub y, so this is u sub xx and this is u sub xx. And u sub y is the same as negative v sub x, and so u sub yy is the same as negative v sub xy, so these two are equal, but because the functions are twice continuously differentiable, the mixed partials are equal, so when I subtract them, I get 0. Okay? And similarly, v sub xx plus v sub yy, for the same reason, equals 0. So what just went away? u sub x, this went away, and this went away. But u sub x v sub x plus u sub y v sub y, that goes away because this is the same as v sub y v sub x because of the Cauchy-Riemann equations, and this is minus u sub y. Is that the way I want to do this? V sub x, that'll do it. But v sub x, u sub y, v sub x is minus u sub y, v sub y and v sub x. Let's do this another way. This is u sub x. V sub x is minus u sub y plus u sub y, and v sub y is u sub x. So once again, I get 0. So u sub x, v sub x plus u sub y, v sub y is 0. And that's the same thing that I have here. So that's 0. So the grand total of this mess is t sub u times u sub x squared plus u sub y squared plus, so I've taken care of that, plus t sub vv times v sub x squared plus v sub y squared, which is equal to, now, u sub y is the negative of v sub x, but when I square it, I get v sub x squared. So that's u sub x squared plus v sub x squared. And the same thing happens here, that v sub x squared is the negative of u sub y squared, so I get but when I square it, it comes out just u sub x squared, and so I get, did I say that right? V sub x is the negative of u sub y. So this is negative u sub y quantity squared, which is u sub y squared, so this is u sub y squared plus v sub y squared. Out of which I can factor this same factor from both sides. Okay? Which is equal to t sub u plus t sub vv times, and of course u sub y squared is the same as v sub x squared, and so I get another u sub x squared plus v sub x squared. All right? But if you remember, since f is equal to u plus iv, this is the derivative of f with respect to x squared. That's actually the absolute value of that. So this is t sub u plus t sub vv times the absolute value of f prime of x squared. Actually, the absolute value of f prime of x. Okay, which, yes, it is squared, which is not 0. This is not 0. So all of this stuff being 0, 0 equals all of this. So 0 equals this. And if this thing equals 0 and this factor is not 0, so that implies T sub UU plus T sub VV must also equal 0, which is exactly what I had to prove. Okay, and of course, all of this argument goes backwards. So those equal signs are two-directional. So we have that if and only if is satisfied. There's a famous, he was a famous algebraist by the name of Emil Artin. If you've ever heard of an Artinian ring, you've heard of Emil Artin. But he was famous for, when he did a lecture, he would start an hour lecture in that corner of a board, and he would write the entire lecture, and at the end of the lecture, he would put a period in that corner. Actually, I did it by accident. He used to do it by planning. But for a few minutes, I was Emil Artin. Okay, so what have we just shown? That analytic functions preserve harmonic functions. Conformal mappings are going to, conformal mappings preserve harmonic functions. Okay. Now, what kind of functions, what kind of mappings are conformal? What are the functions that have this cool property that the derivative is not zero through a region? So we're going to take a look at several examples of little monsters like that. Now, earlier, we saw that the upper half plane in the complex plane, the upper half plane, so where y is positive, with its border the x-axis, union the point at infinity. So we did toss that one point on there. It's a beautiful structure in topology, by the way, called the one-point compactification. But you don't need to know that. We just studied it in topology, though. So that the upper half plane with its border, the x-axis union the point at infinity, is mapped one-to-one onto the unit disk with its border. Now, that may not seem terribly exciting, and I think I pointed this out at that time, but I want to point it out again simply because compact sets, you studied those in calculus, and we've studied them a little bit here. A compact set, at least in Euclidean space or in the complex plane, is a set that's closed and bounded. The upper half plane is neither. It's not closed, it's not bounded. And so if I can take that set and I can map it conformally, preserving angles, right? I map it conformally into a compact set, namely that unit disk with a boundary, closed and bounded, right? Then I can do a lot of stuff over here that I couldn't do over here. And then after I do the stuff, because of the theorem I just proved, the nice features of any function that I'm dealing with over here, they can be pulled back to over here and the harmonic feature is preserved. That's a big, big deal to be able to do your stuff over here in a compact set. So, and what function did we use? Do you remember? The conformal mapping that we used was W equals, I call it A or alpha, Z minus A over Z minus A bar, complex conjugate of A. And so that mapped the boundary, the x-axis, to the boundary over here, the unit circle, and it mapped the upper half plane to the interior inside that unit circle, the unit disk. And we showed you that the other day. So this is a conformal mapping. It satisfies the required condition that the derivative is not zero. So let me ask you this: what other can I generalize this? Well, we generalize it with what are called bilinear transformations. This is a bilinear transformation, and as it turns out, bilinear transformations are conformal. So, W equals alpha Z plus beta divided by gamma Z plus delta. Does everybody see that this has that form? Okay, this is a bilinear transformation where alpha is equal to 1, gamma is equal to 1, beta is equal to negative A, and delta is equal to negative A conjugate. Okay, so this is a bilinear transformation. And these are conformal if alpha times delta minus beta times gamma is not zero. Okay? If that's not zero. Now, by the way, those of you who are familiar with linear algebra probably recognize right away that that's the determinant of this matrix. Alpha delta minus beta gamma. Okay? And the proof of that ain't hard. Let's prove it. What is f prime of z? Well, you know how to do this. This is the quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared, which is copy, 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 squared. Okay, so that is equal to, now, here I've got alpha gamma z minus alpha z gamma. And the people all said, did you say poof? Were you really honest and you said poof? Well, that goes bye-bye. So what am I left with? Alpha delta minus beta gamma divided by the bottom squared. And this is not zero if the determinant of alpha, beta, gamma, delta is not zero. Okay? So, these bilinear transformations are nice little monsters. They're conformal mappings. Okay. Well, now here's what I want to do, and this isn't going to take terribly long. Let's see, there's one other thing that I wanted to do here. Now, I want to show you several different kinds, though. What kinds of mappings are here? So these are examples. Suppose that W equals alpha Z. Is this one of those? And the answer is yes, because alpha Z is this if beta is 0, gamma is 0, and delta is 1. That's exactly this. So this is a bilinear transformation. Okay, what does it do? What does multiplying a vector by a scalar do? And the answer is it scales it. Okay, that's why they're called scalars. You multiply by it, might make it a little smaller, might make it a little bigger, it might, might change it a bit, move it around a bit. But if alpha is a real number, if it's a positive real number, let's look at what happens to a rectangle. So in the z-plane, where this is x and this is y, we might have this little rectangle here, where this is 1, this is 1i, and here's my rectangle. Okay, what happens when this function, multiplying by a positive real number, what happens when I do that? And the answer is, it gets bigger if alpha is bigger than 1, or it gets smaller if alpha is less than 1. So we'll pretend that it's bigger than 1 in this case. And that's what happens under W equals alpha Z. Okay. Or smaller if, like I said, alpha is between 0 and 1. What about, now, alpha can be a complex number. Okay, let's suppose that it's a complex number whose absolute value is 1. Okay, so what do those look like? Alpha equals e to the I theta. Right, absolute value of this is always 1, no matter what theta is. So what's going to happen here? It's going to be the same size, because the absolute value of this is 1, but e to the I theta, that's going to turn it by an angle of theta. Okay, so it's going to rotate it. Now what happens if I multiply by an arbitrary, if I multiply it by an arbitrary complex number, z? So if alpha equals r e to the I theta, remember that every complex number can be written in this form, right? So r now is a non-negative a non-negative real number. And of course, if r is equal to 0, the whole thing collapses to a point, and that's not really very interesting. It doesn't have an interior. But if r is positive, as we had over there, that alpha was positive, then that's going to scale it. This is going to turn it. And so what happens to this little rectangle over here? Well, both things are going to happen to it. It's going to scale it, and it's going to turn it. Okay? Actually, this point here should be at the origin. I'm not the greatest artist here. I'm going to move the axis. That's cheating. Okay, so there's my y-axis. It's going to turn it, and it's going to scale it. Okay? Now, all of these have that form of alpha z plus beta divided by gamma z plus delta. Okay? So, and this, of course, is still alpha z, where alpha now has scaling and rotation. All right, let's try alpha z plus beta. What's that going to do? And I'll bet you can see it. The physicists have already seen it. The alpha z is going to scale it and turn it, and beta is going to translate it to someplace else. Okay? That's what happens with alpha z plus beta. Now, what's another thing that could happen with W equals alpha z plus beta divided by gamma z plus delta? What if alpha is 0, and beta is 1, and gamma is 1, and delta is 0? So if alpha equals 0, beta equals 1, gamma equals 1, and delta equals 0, so still that determinant is not 0, right? It's -1, and when you take the absolute value, you get a positive number. But what happens now? Now W is equal to 1 over z. What does 1 over z do to our little rectangle? And the answer is, actually, rather than to do a rectangle, I'm going to do the example that we started with, a unit disk, because that's really the most interesting. So if I start with the unit disk, see, I need to move the axis again. Last time I went to the left, this time I went to the right. At least it came out even at the end. So if I take this disk, and I'm looking at the interior of that disk, and maybe I've got another disk out here. In fact, let's make that one blue. Got all these colors here, and I'm not using them. Okay, let's make that one blue. What happens when I invert the function? And the answer is, I turn this inside out. The inside of this becomes the outside, and the circle that was outside, its image under this transformation is now inside. And that's what happens when we invert these little monsters. So One more thing I want to show you. It's called an eraser. No, that's not what I want to show you. Let's do a specific example. W equals z minus I over. Now remember that the original transformation I showed you was z minus a divided by z minus a bar conjugate. What's the conjugate of I? It's minus I. So this is going to be z minus I bar, which is z plus I. So let's see what this transformation does. Where, and we know about the upper half plane and all of that, but I want to know exactly where everything goes. Where does everything go under that transformation? Well, first, let's see where the x-axis goes. If we're on the x-axis, then y, of course, is equal to 0. The vertical axis is 0. Okay? So now, since z equals x plus iy, that's going to, I'm sorry, yeah, z equals x plus iy, but y is 0, so this is going to be x minus I over x plus I. So, let's compute the absolute value of w. That's going to be the absolute value of this quotient. Which is equal to the square root of the sum of the squares of these coefficients. So that's just x squared plus y squared. And the bottom is also x squared. I'm sorry, x squared plus 1. The coefficient in front of I is -1. When I square it, I get +1. Coefficient here is 1. So that's x squared plus 1 over x squared plus 1, which is 1. So where does the x-axis go? It goes to the unit circle, which is what we claimed. Okay? So x-axis is transformed to the unit circle. Now, what did I call this point? Let z be in the upper half plane, which the other day I called h. Okay? I'll label it again, the upper half plane. All right, so let z be in h. Then, where does z go? Well, the absolute value of z plus I is equal to the absolute value of x plus iy plus I, which is equal to the absolute value of x plus I times y plus 1, which is equal to the square root of x squared plus y plus 1 squared. Okay? And what about the numerator? I did the denominator first. What does the numerator look like? Well, z minus I is equal to absolute value of x plus iy minus I, which is equal to absolute value of x plus I times the quantity y minus 1, which is equal to the square root of x squared plus y minus 1 quantity squared. Okay, now I claim that this is smaller than that. Let's take a look. It's easy to see. but x squared plus y squared, y plus 1 squared is greater than x squared plus y minus 1 squared, because I have an x squared on each side, so that goes poof. I've got y squared plus 2y plus 1 is greater than y squared minus 2y plus 1, because these go poof, and this is because 2y is greater than minus 2y, and that's because in the upper half plane, y is positive, and a positive number is always greater than a negative number. Therefore, if z is in the upper half plane, the absolute value of w is less than 1, right? Because it's equal to the smaller one divided by the bigger one. So the upper half plane without the boundary, without the x-axis, goes to the interior, the open disk, the interior of the unit disk. Okay, so the whole half plane ends up inside. Okay. Now, where does I go? Now, I is in the upper half plane, right? Right there. So it's in the upper half plane. Where does it go? Well, I know it goes someplace into the unit disk. Where in the unit disk? Well, let's take a look. What is f of I? When you plug I into the function, you find out it goes to 0. F of I is equal to 0. So I goes into the origin. Okay. Where does the point at infinity go? Where does infinity go? Well, as z goes to infinity, this little number and this little number here are chicken feed. So this whole thing approaches 1. And that's exactly why I need the point of infinity to fill this point in. Okay? Where does 0 go? 0 is on the x-axis. Well, if z is equal to 0, then I get 0 minus I over 0 plus I, which is equal to minus I over plus I, which is equal to, well, the i's cancel obviously, and that's negative 1. So the other side is where 0 goes. And finally, another point of interest that's on the x-axis. Wonder where that goes. F of 1 is equal to 1 minus I over 1 plus I. And when you divide by a number, if you want to make it a real result in the denominator, which is often the case, you multiply and divide by the conjugate of the bottom. So I've got 1 minus I over 1 plus I, but then to make the bottom real, I'm going to multiply by 1, but this is my name for 1. 1 minus I divided by itself is certainly 1. But when I multiply by that, what do I get in the denominator? I get 1 plus I minus I, and the people all said, yeah, poof. And then minus I squared, but I squared is negative 1. So minus that is plus 1. So this is 1 plus 1, which is also called 2. And what's on top? 1 minus 2i plus I squared, which is minus 1, which is, of course, the 1 minus 1 goes poof, the 2's go poof, and I get minus I. So, on the unit circle, where does 1 go? It goes to minus I. Okay? And that's where all the interesting points go. So, under this transformation, handy little transformation, taking this unbounded big old set and packing it inside the, pardon the pun, the compact set, the unit disk with its boundary. And I am to the end of the information that we are to do this semester. And so God bless every one of you. Finish well. Hang in there to the end. That's advice not only for complex variables, not only for mathematics, but that advice is for your entire Christian walk too. When you marry someone, hang in there to the end. When you have children and your children are disappointing you and they're making you mad, oh, I've got 4 kids. You think that never happened to me, that I wasn't disappointed and didn't have problems with them? But I hung in there and I loved them to the end, and they all knew it. And now they're godly men serving the Lord. I've got grandchildren. They're raising them for the Lord. And finally, in your own personal Christian walk, hang in there to the end. If you're saved, if you have really, sincerely had Jesus come into your heart, then you're saved. You're going to heaven. But finish well there too. Run the race, as Paul said, run it to win. Run it to finish. God bless you, and bye-bye.